Okay, for this question, we're going to look at the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared. Now, how can we do this? What's our usual strategy for evaluating these limits? Well, we typically consider different pathways. So let's consider points that are going along the x-axis. Where are they headed? And that is, of course, along y equals 0. If I'm approaching along y equals 0, that is the limit as x0 approaches 0, 0 of what? 3x squared times 0 over x squared plus 0 squared, which is the limit as x approaches 0 of 0 over x squared, which is 0. Okay. How about along the line x equals 0, which would be coming this way? Along the line x equals 0, what would that be? That's the limit of 0 comma y approaches 0 comma 0. X is 0, so that's 3 0 squared times y over 0 squared plus y squared, which is the limit as y approaches 0 of 0 over y squared, which is 0. So we have shown two paths that yield 0. Is that enough to prove that the limit equals 0? No. So shall we try another one? How about along the line y equals x? What's going to happen there? Approaching from both sides, it's heading towards 0, 0 along the line y equals x. Is that going to give us a different value? If it does, then the limit doesn't exist. But if we get 0, we have to determine what that tells us. So xy approaches 0, 0, but this time y equals x. So we're going to write that as the limit as xx approaches 0, 0 of 3x squared times x over x squared plus x squared squared, which is the limit as x approaches 0 of 3x cubed over x squared plus x to the 4. And what should we do here? We have a 0 over 0 case, so we can use L'Hopital. So using L'Hopital once, we get the limit as x goes to 0 of 9x squared over 2x plus 4x cubed. We still have 0 over 0. We could do L'Hopital again, equals the limit as x goes to 0 of 18x over 2 plus 12x squared. Now we have 0 over 2. So that also equals 0. So we've shown three different pathways. We could keep looking for others, but we might think that based on our work so far, that there's a chance that this limit exists. So how do we prove that a limit exists? Now, back in earlier calculus courses, you may have used an epsilon delta sort of argument. And yes, you can approach this problem with that strategy, but I think it's better to reconsider a different coordinate system, and that will be the polar coordinates. So here we go. And what do we recall? In our polar coordinate system, this is x, this is y, this is r, and this is theta. So cosine of theta is x over r. So r cosine theta is x. Sine of theta is y over r. So r sine theta is y. And what about r? Well, we know x squared plus y squared is r squared. Fine. We know that. But more importantly, if xy is approaching 0, 0, if we have these dots getting closer and closer to 0, what's happening there is that r, the distance from the origin, r is getting closer and closer to 0. So we can write this in the following format, making our substitution. Instead of the limit as xy approaches 0, 0, I'm going to say the limit as r approaches 0. Instead of x, we're going to say 3 r cos theta squared. Instead of y, we're going to say r sine theta. And downstairs, x squared plus y squared is r squared. So this is interesting. We're looking at the limit as r goes to 0, but there's both r's and thetas here. So how can we approach this argument? Well, let's collect things a little bit. This in turn equals the limit as r goes to 0 of 3 r squared r, so that's r cubed, cos squared theta, sine theta, over r squared. And of course, the r's divide out, so now I get the limit as r goes to 0 of 3r cos squared theta sine theta. So can we solve that? How do we manage the thetas? What's our strategy we're going to use there? And the key to that is to recognize that sine theta only gets as large as a certain number, only gets as small as a certain number. And the same thing is true for cosine squared theta. So keeping that in mind, does that enable us to come up with something? So here we are, and what do we know? We know sine theta is always less than or equal to 1 and greater than or equal to -1. That's going to be important. Now, cosine squared theta is also less than or equal to 1. It's greater than or equal to 0, but it's not going to hurt me to say that it's greater than or equal to -1. That's also true. So what can we say about cosine squared theta times sine theta? There's no way this gets any bigger than 1, and there's no way this gets any smaller than -1. And that will be sufficient for us to determine how this limit is going to work. Because this is what we have. Again, our goal is the limit as r goes to 0 of 3r cos squared theta sine theta. Let's write that down. 3r cos squared theta sine theta. This is less than or equal to 3r times 1. Cos squared theta sine theta is less than or equal to 1 and greater than or equal to 3r times -1. So we get this important fact. Now, is this enough for us to determine what the limit will be as r goes to 0? So think about that for a second. As r goes to 0, what happens here? As r goes to 0, what happens here? As r goes to 0, what happens here? Well, as r goes to 0, 3r goes to 0. Similarly, as r goes to 0, -3r goes to 0. And this is squeezed in between two things that head towards 0. Therefore, by the squeeze theorem, that limit has to also be 0. So what do we conclude? By the squeeze theorem, we get this fact. But remember, this was equivalent to our original question, which was the limit is xy goes to 0, 0 of 3x squared y over x squared plus y squared. So our real conclusion to this is that we've proven that that limit with the x's and y's, 3x squared y over x squared plus y squared, has got to equal 0. So any idea how this graph is going to behave as those xy values get closer and closer to 0? Well, let's take a look at Desmos to get a visual of that graph. So what do we see? Is the surface always heading towards 0, 0, all paths heading towards 0, 0? Looks that way to me. Looks that way to me. So indeed, that reinforces the notion that our limit as xy approaches 0, 0 of this function is indeed equal to 0.